Hey, I'm Nick Barna. My partner is Jordan Gibbs, and we did our CFD final project on the Magnus effect. The Magnus effect is a phenomenon in which a rapidly rotating object in a fluid experiences drag and lift. The lift created by the spinning object is perpendicular to the direction of the flow and the axis of the rotation. This force significantly affects the flight of the object and is commonly observed in objects such as golf balls and baseballs. Shown here, a spinning basketball dropped from a significant height creates enough lift to yield a nearly horizontal flight path. Pressure and velocity differentials are crucial for lift generation. The angular velocity of the Magnus effect creates an area of high pressure and low velocity beneath the spinning object and low pressure, high velocity above the object. These forces push upward on the spinning body and create lift. So basically, a spinning object can create lift. So now I'll talk a little bit about our methods for our simulations. They were created in star CCM, and we were studying a couple different geometries. So we created a 5 by 5 meter square, and that was the fluid flow field. Then we took a 1 meter diameter circle and we subtracted it from the surface to act as a spinning region. Then a 1 meter circle was created to plug the subtraction. And then the polygons were subtracted in a second operation from the plug. So the initial circle geometry that we used had a diameter of 0.5 meters, and each of the polygons they were circumscribed within a 0.5 meter circle. We did triangular, square, hexagonal, octagonal, and decagonal and circular geometries. So the circular geometry was used as our control for the experiment because we know that it gives us a nominal Magnus lift value for our given flow velocity. So then we took these shapes and we spun them at 300 RPM clockwise, and they had a no-slip condition at the wall. So then for our fluid flow setup, we had left-hand wall, the 5 by 5 meter square was a velocity inlet of 2 meters per second, and the right-hand wall was set as a zero pressure outlet, and that's to help the convergence rates of each simulation. The top and bottom edges were set to a wall condition, and this was a transient turbulent simulation in constant density water. So water was our media for this experiment. We made it a turbulent model because the Reynolds number for our setup is about 1.6 times 10 to the 6th, so right on that turbulent range. And the time step was 5.5 times 10 to the minus 4 seconds, and with a 12 inner iteration maximum. So each simulation was run until the lift monitor on the polygon walls converged to a relatively constant value. So we just ran the simulations until our lift monitor leveled out. For our mesh, we made 2D meshes for each fluid field. So we had a base size of 0.01 meters, default surface growth rate of 1.3, and then we had a boundary relax applied, and that was to reduce the amount of elements in the outer sections of the flow field and to create a clear interface between those. We also had a wake refinement between the geometry of the plug, and that was in the X direction with a 15-degree spread, 100% base size, and a 1.3 growth rate. And we also applied a 2D mesh to the plug field, and that had the same base size and the same growth rate. We also had a uniform control to make each element similar in area. And we had 25 prism layers to the walls of each polygon, and they had a stretch factor of 1.2.
For the results of the simulations to be accurate, it was essential that the models were structured to be iteratively solved for a transient solution of the Magnus effect. Earlier trials of steady-state solutions were not indicative of real-world effects and often would fail to model the Magnus effect in any capacity. The transient solutions, while computationally intensive, proved to be the best option to reflect physical validity. Our results for this experiment were closely compared to a paper written on the same subject matter by Santiago Pizzotti, where these same polygons were studied in a wind tunnel. Two important differences are the Reynolds numbers and the tip speed ratios. Our Reynolds number was in the realm of 1.6 times 10 to the 6th for each simulation, whereas Pizzotti's was a maximum of 3.5 times 10 to the 4th. Our tip speed ratio is set to 3.9, which according to a 2003 paper by Mittal and Kumar is reasonable for the Reynolds numbers obtained by our simulation, and is consistent with other research done on cylindrical Magnus lift. The tip speed ratios in Pizzotti's study were between 0.2 and 0.9. These differences are important to point out, but this can explain any inconsistencies between the models. This shows the velocity field of the circle. The high velocity region on the top of the circle generates lift as expected. According to nasa.gov, the lift force of a circle under these conditions is 24,590 newtons. The circle simulation gave 7,500 newtons of peak lift based on the y-axis lift report placed on the edge of the circle. This is quite far off from expected, but this is probably due to the simplified conditions of the simulation. If there was more computing power available, this number could have been closer to the theoretical. This circle simulation is used as a reference to the rest of the polygons. It is a good baseline for the lift values that should be expected. This is the velocity field development of the triangle. The sharp edges of the triangle act as scoops that carve up through the fluid and create pockets of high velocity and low pressure along the top edge. This can be seen here, which is an animation of the absolute pressure of the triangle throughout the simulation. The lift monitor picked up a maximum value of 9,500 newtons, which is significantly higher than the circle. The Pezzati paper did not examine a triangle, so there is no real-world data to compare this to. We initially hypothesized that the triangle would be less efficient than the circle due to the trailing edge effects, but this is clearly wrong. Similar to the triangle, the square's sharp edges create low pressure pockets at the top edge of the spinning region. This creates 15,000 newtons of lift, which is roughly double that of the circle. This aligns with the empirical data garnered in the Pezzati paper. In these experiments, the team found that the lift values for the square section are up to 2.5 times higher than that of a circle, depending on the tip-speed ratio. This supports our model's validity. This shows the hexagonal test. This gave lift values of 17,400 newtons, which is significantly higher than that of a circle. This value does not align with the Pezzati paper. The observed lift coefficients of the hexagonal cross-section were actually close, 2.2 times the higher than that of the circle, as opposed to this model which gave us a value 2.32 times that of the circle. However, this is higher than the square's lift, which is unexpected. This is the octagonal test velocity field. The maximum lift seen here is 13,500 newtons. According to Pezzati's results, this should be roughly the same amount of lift as the hexagonal section. However, this is 22% lower, which is unexpected. In the paper, the hexagon, octagon, and decagon were all very consistent with one another in terms of lift coefficient, as can be seen in this figure. The square is a bit of an outlier in this data, but the consistency between the 6, 8, and 10-sided polygons can be seen. Compared to the hexagonal data, this is more consistent with what we were expecting. The decagon test ran as expected and garnered a lift value of 11,300 newtons. This is only 1.5 times that of the circle, which is lower than what Pezzati describes. As the geometry gets closer to that of a circle, the lift value should end up being similar to it. Further research could be done on n-gons with 20 plus sides to see if there is a point where the circle is effectively no different in lift. Eventually, the edges will have a little to no effect of the flow around the object. It will be effectively round. This was not explored due to the extreme lengths of these simulations. Each simulation took 8 to 12 hours to run, and that does not include the failed trial runs. This graph shows the lift data for all the simulations side by side. There is a visible bump in the forces in the hexagon and octagon range, but the square, in order to align with Pezzati's results, should be the highest. There are a number of reasons for this discrepancy, but the most likely culprit is the tip-speed ratio of 3.9. While this was proven to be a reasonable ratio for the Magnus effect, our model created lift coefficients in the square, hexagon, octagon, and decagon that exceed that of the Prandtl maximum lift coefficient of 4 pi. This has been proven to be exceeded in certain flow situations, however, this is not well understood. Ideally, in future simulations, this should be accounted for and sufficiently adjusted so that this lift ceiling is not exceeded. Holistically, the lift created by the different model geometries aligns with the experimental results, and show an increase in lift for rougher surface geometries, i.e. triangles, squares, and hexagons will create more lift in the circle at the same angular velocity. However, the precise lift values produced from the simulations differ from the experimental values obtained in a wind tunnel with identical geometries. This could be due in part to the difference in tip-speed ratios, as the CFD model was simulated with a tip-speed ratio of 3.9, compared to the Pezzati study, which analyzed the same geometries for tip-speed ratios from 0.2 to 0.9. The STAR CCM Plus models confirmed higher lift forces for bodies with rougher surface geometries, but failed to predict lift coefficient values that were consistent with the available scientific literature. To create more accurate simulations, experimentation with different physics values and flow fields would need to be explored. A constant density model was used for the water in the simulation to speed up the simulations. The Pezzati research was performed in air, which is highly compressible. Another improvement would be to increase the mesh density. Each simulation had roughly 45,000 elements, but this should be increased to 10 times that for ensured accuracy. While not perfect, The star CCM plus simulations of Magnus lifts is a valid model for the real world.